Yeah, it's Robert Ganzi here again with Alum video number 3. So, to start off the video like normal, taking a look at the alum crystals. So, here are the alum crystals. So, other size, they haven't really grown that much larger since the last video. They're actually still relatively similar in size. So, I think like this is very likely due to the fact that they've possibly already used up all of the alum in this solution. It's already all like crystallized down, and while it's possible that hasn't happened, I think that might be a likely reason why they've all stopped growing. So one of the problems we were given is how we would create a big crystal, a very large crystal. So the method of doing that would be that you let the crystals form like normally as we did here. So you do this. Then you find like one of the largest crystals of these smaller crystals, and you take that crystal and you use it as a seed crystal to grow a very large crystal. So the way you do that is you take this crystal, you put it in the solution. You want it to not be touching the walls, so you'd like hang it down so it wouldn't have any other places, any other nucleation sites where crystals would form. They'd all just form on this crystal. Then you would get a nice like alum solution. You put this like the biggest of your small crystals in the solution, and then all the crystals would all the alum in solution would cling onto it and cause the crystal to grow larger and be rather high quality.
1 second.
So.
And for that class.
Yeah. So after that we need to talk about the Bragg's law of d-spacing in order to determine the structure of this crystal. So what d-spacing is basically when atoms are in a structure like a crystal, they're like in set planes apart from each other. So we can use a certain formula to find the distance between these two planes, which we'll discuss in a little bit. So d-spacing describes the distance between these planes, and this is useful to us because it allows us to create a unit cell from this information from this D. We can create like a unit cell of the crystal structure. In the crystal formation we can like generate the crystal just from this data, and this is helpful for us for creating crystals as well because every crystal has its own unique pattern. So every substance is going to be different. So we can use that to like find the differences between all of these substances, which is pretty cool. So Bragg, this guy Bragg created this formula, 2d times sine of theta is equal to n lambda, where basically he used X-ray waves in order to determine this distance d right here. So what we do first is we're going to solve for d, so we find d is equal to n lambda over 2 sine theta. And then looking at the X-ray diffraction chart we were given for alum, I estimated that the highest peak was around 20.52 theta, and then divide that by 2 because it's 2 theta, and we get it's around 10.25 degrees. And then looking up the lambda for an X-ray, I found the wavelength to be around 10 to the negative 10th. There's a little bit of range there though, so that might not be completely correct. I wasn't sure exactly what to do in that situation, so I just took like a value that seemed appropriate. So for n is just a number that's a whole integer of the wavelength. So what that means is, because based on the way the formula works, the X-rays need to be going out in phase in order to be like properly detected. So because of that, this n has to be a whole integer of the wavelength. So because there were so many counts for the 10.5 degree mark, I assumed that there would probably be at least one that had one wavelength. It was just 1 times the wavelength, so I used 1 for n in this situation. But that might have not been correct, so that would completely throw off the numbers. But I'm rolling with that. So then you do some math, and you find that d is equal to 2.81 times 10 to the negative 10th meters, which means that's what this distance is. And we can use that distance to find a unit cell and generate a crystal structure, which is pretty cool. Alright, so this has been alum video number 3, the final alum video. And yeah, hope you enjoyed it.